ML, ML, guys, machine learning, deep learning, machine learning, yeah, machine learning, guys. Andrew NG, Andrew NG, Andrew NG, machine learning, Andrew NG, internship, money, Andrew NG, my playlist. La, this is what is. We are looking for it right now. Middle of the session 11. We are. Let's go, guys. Click.
So what the network is probably going to do is it's probably going to send this one to one half.
So we have 3 goals.
Probably, which is not what you want.
With the good teacher, which is very patient and ask questions.
Let's talk about the loss function for this softmax regression.
For this, Ctrl+Shift+2. Welcome, guys.
Because you know what's interesting about this loss is if I take this derivative of the loss 3n with respect to W21. Do you think it's going to be harder than this derivative, than this one, or no? It's going to be exactly the same, because only one of these 3 terms depends on W12. It means the derivative of the 2 others are 0. So we're exactly at the same complexity during the derivation. But this one, do you think if you try to compute, let's say we define a loss function that corresponds roughly to that. If you try to compute the derivative of the loss with respect to W2, it will become much more complex, because this number, the output here, that is going to impact the loss function directly, not only depends on the parameters of W2, it also depends on the parameters of W1 and W3. And same for this output. This output also depends on the parameters W2. Does it make sense? Because of this denominator. So the softmax regression needs a different loss function and a different derivative. So the loss function we'll define is a very common one in deep learning. It's called the softmax cross entropy. Cross entropy loss. I'm not going into the details of where it comes from, but you can get the intuition of YK log.
Cross entropy. Oh, that is entropy. Yeah.
So it surprisingly looks like the binary the logistic loss function. The only difference is that we will sum it up on all the classes. Now, we will take a derivative of something that looks like that later, but I'd say if you can try it at home on this one, it would be a good exercise as well. So this binary cross entropy loss is very likely to be used in classification problems that are multi-class. Okay, so this was the first part on logistic regression types of networks. And I think we're ready now with the notation that we introduced to jump on to neural networks. Any question on this first part?
Yo, neural networks. Let's go. Don't touch my phone.
So one question I would have for you. Let's say
my wallet.
Instead of trying to predict if there is a cat or no cat, we're trying to predict the age of a cat based on the image. What would you change? This network. Instead of predicting
I love it.
0,
This guy asks questions
based on the image. What would you change? This network. Instead of predicting 1, 0, you want to predict the age of a cat.
Age of
What
a
are the
cat?
things you would change?
What do you mean 1, 0, age of a cat?
Yes. Okay, so I repeat, I basically make several output nodes where each of them corresponds to one age of cat. So would you use this network or the third one? Would you use the 3 neurons neural network or the softmax regression? The third one, why?
Softmax, because
You have a unique age. You cannot have 2 ages.
2 ages,
Right.
exactly.
So we would use a softmax one because we want a probability distribution along the edge, the ages. Okay, that makes sense. That's a good approach. There's also another approach which is using directly a regression to predict an age. An age can be between 0 and plus infinity, not plus infinity, but 0 and a certain number. And so let's say you want to do a regression. How would you modify your network? Change the sigmoid. The sigmoid puts the z between 0 and 1. We don't want this to happen. So I'd say we will change the sigmoid. Into what function would you change the sigmoid?
M times sigmoid. Multiply it.
Yeah, so the second one you said was? Oh, to get a Poisson type of distribution. Okay, so let's go with linear. You mentioned linear. We could just use a linear function, right? For the sigmoid.
Yes.
But this becomes a linear regression. The whole network becomes a linear regression. Another one that is very common in deep learning is called the ReLU function. It's a function that is almost linear, but for every input that is negative, it's equal to 0. Because we cannot have negative age, it makes sense to use this one. Okay? So this is called rectified linear unit, ReLU. It's a very common one in deep learning.
Rectified.
Now, what else would you
linear
change? We talked about
unit.
linear regression. Do you remember the loss function you were using in linear regression? What was it? It was probably one of these two. Y hat minus y. Just comparison between the output label and y hat, the prediction. Or it was the L2 loss. Y hat minus y in L2 norm. So that's what we would use. We would modify our loss function to fit the regression type of problem. And the reason we would use this loss instead of the one we have for a regression task is because in optimization, the shape of this loss is much easier to optimize for a regression task than it is for a classification task, and vice versa. Not going to go into the details of that, but that's the intuition. Okay, let's go have fun with neural networks.
Look at his mindset. Have fun. Not that I want to teach you fucking neural networks and splash neural network in your face.
So we stick to our first goal. Given an image, tell us if there is cat or no cat. This is 1, this is 0. But now we're going to make a network a little more complex. We're going to add some parameters. So I get my picture of the cat. Cat is moving.
Cat is moving.
Okay? And what I'm going to do is that I'm going to put more neurons than before.
Neurons was
Maybe
the
something like that.
sigma wx plus b or just the wx plus b? I don't know. New ones. Oh, multi-layer.
So using the same notation, you see that my square bracket here is 2, indicating that there is a layer here, which is the second layer. While this one is the first layer and this one is the third layer. Everybody's up to speed with the notations? Cool. So now notice that when you make a choice of architecture, you have to be careful of one thing. Is that the output layer has to have the same number of neurons as you want the number of classes to be for a classification. And
Yes.
1 for a regression. So how many parameters does this network have? Can someone quickly give me the thought?
So the photo times 3. All right. Three, then plus like 6 plus 3, something like that.
Thought process. So how much here? Yeah, like 3n plus 3, let's say. Yeah, correct. So in here, you would have 3n weights plus 3 biases. Here, you would have 2 times 3 weights plus 2 biases, because you have 3 neurons connected to 2 neurons. And here, you will have 2 times 1 plus 1 bias. Make sense? So this is the total number of parameters. So you see that we didn't add too much parameters. Most of the parameters are still in the input layer.
No,
let's
the
define some
bias.
vocabulary. The first
Oh, okay, I got it. 2 times 3 because we have 2 nodes at the like first layer, second layer. We have 2 nodes at the second layer. So 2 times 3, this is the 2. 3 is the 3 number of the nodes in the first layer. And plus 2 because each node in the second layer needs a node. And 2 times 1 plus 1 is because we have 2 nodes in the first layer, a second layer, 1 node in the third layer, so it is 2 times 1. We have 1 node in the third layer plus 1 bias.
first word is layer. Layer denotes neurons that are not connected to each other. These 2 neurons are not connected to each other. These 3 neurons are not connected to each other. We call this cluster of neurons a layer. And this has 3 layers. We would use input layer to define the first layer, output layer to define the third layer because it directly sees the output, and we would call the second layer a hidden layer.
Hidden layer.
And the reason we call it hidden is because the input and the outputs are hidden from this layer.
So, okay, we could have a simpler, just 2-layer network. Is it called neural network? I don't know. What is the difference with this having an extra layer? With that one, we had a sigmoid function from each node input to the output, right? Now we are just like, again, giving it to some sigmoid function, linearize, like get an affine linear function out of these sigmoids and take it as input to another sigmoid function. So it seems we are, wow, black pepper. It seems by combination of sigmoid functions, layers of sigmoid function, and a linear function, we are getting better estimates of like input-output relation. That's it, right? We have a more complex model for sure, so we probably can do more computation. Probably we can't do that because we have the ability to do the computation. And for sure, this is more complex. It can solve more. It can be more exact or have a better. What is it called? Have a better convergence. Not convergence. Something like that. The metric that a machine learning system is good.
It means the only thing that this layer sees as input is what the previous layer gave it. So it's an abstraction of the inputs, but it's not the input. Does it make sense? And same, it doesn't see the output. It just gives what it understood to the last neuron that will compare the output to the ground truth. So now, why are neural networks interesting? And why do we call this hidden layer? It's because if you train this network on cat classification with a lot of images of cats, you would notice that the first layers are going to understand the fundamental concepts of the image, which is the edges. This neuron is going to be able to detect this type of edges. This neuron probably going to detect some other type of edge. This neuron may be this type of edge. Then what's going to happen is that these neurons are going to communicate what they found on the image to the next layer's neuron. And this neuron is going to use the edges that these guys found to figure out that, oh, there are ears. While this one is going to figure out, oh, there is a mouth. And so on, if you have several neurons. And they're going to communicate what they understood to the output neuron that is going to construct the face of the cat based on what it received. And be able to tell if there is a cat.
Nice intuition.
So the reason
we
it's
are
called
breaking
hidden layer
cats
is because we don't really know what it's going to figure out.
So
but with enough data, it should understand very complex information about the data. The deeper you go, the more complex information the neurons are able to understand. Let me give you another example, which is a house prediction example. House price prediction.
So once we have more layer, I guess it's better because we can break the task of finding cat in simpler steps for the computer, and then we have better results. That's the idea, right? Is there a
So
trade-off?
let's assume that our inputs are
Is there a sweet
number
spot that the number of layers
of
the best?
bedrooms, size of the house, zip code, and wealth of the neighborhood, let's say. What we will build is a network that has 3 neurons in the first layer and 1 neuron in the output layer.
Bedrooms, size.
So what's interesting is that as a human,
What
if
is
you
the
were to
difference
build
between zip code and wealth?
this network and like hand engineer it, you would say that, okay, zip code and wealth sorry, wait a minute, let's do that. Zip code and wealth are able to tell us about the school quality in the neighborhood. The quality of the school that is next to the house, probably. As a human, you would say these are probably good features to predict that.
Everybody's
The
like,
zip
no.
code is going to tell us if the neighborhood is walkable or not. Probably.
Zip code. Okay.
The size
Gangsters are there.
and the number of bedrooms is going to tell us what's the size of the family that can fit in this house. And these 3 are probably better information than these in order to finally predict the price. So that's a way to handle.
Yes, okay, so look, the information we have on the second layer are not observable right now, but the first layer information are observable. That's the important thing. We can only act based on the information that we observe, while they may not be the root cause.
Engineer that by hand as a human in order to give human knowledge to the network to figure out the price. In practice, what we do here is that we use a fully connected layer. Fully connected. What does it mean? It means that we connect every input of a layer, every input to the first layer, every output of the first layer to the input of the third layer, and so on. So all the neurons among from one layer to another are connected to each other.
Still, we can't do that.
What we're saying is that we will let the network figure these out. We will let the neurons of the first layer figure out what's interesting for the second layer to make the price prediction. So we will not tell these to the network. Instead, we will fully connect the network and so on. Okay? We'll fully connect the network and let it figure out what are the interesting features. And oftentimes, the network is going to be able, better than humans, to find what are the features that are representative. Sometimes you may hear neural networks referred as black box models. The reason is we will not understand what this edge would correspond to. It's hard to figure out that this neuron is detecting
variable
a weighted average
may not have
of input features.
Meaning in real life.
Make sense?
Just a combination of it.
Another word you might hear is end-to-end learning. The reason we talk about end-to-end learning is because we have an input, a ground truth, and we don't constrain the network in the middle. We let it learn whatever it has to learn. And we call it end-to-end learning because we're just training based on the input and the output.
Okay.
Let's delve more into the math of this network. The neural network that we have here, which has an input layer, a hidden layer, and an output layer. Let's try to write down the equations that run the input and forward propagate it through the output. We first have Z1, that is the linear part of the first layer, that is computed using W1 times X plus B1. Then this Z1 is given to an activation, let's say it's sigmoid, which is sigmoid of Z1. Z2 is then the linear part of the second neuron, which is going to take the output of the previous layer, multiply it by its weights, and add a bias. The second activation is going to take the sigmoid of Z2. And finally, we have the third layer, which is going to multiply its weights with the output of the layer preceding it and add its bias. And finally, we have the third activation, which is simply the sigmoid of Z3. So what is interesting to notice between these equations and the equations that we wrote here is that we put everything in matrices. So it means this A3 that I have here, here, for 3 neurons, I wrote 3 equations. Here, for 3 neurons in the second layer, I just wrote a single equation to summarize. But the shape of these things are going to be vectors. So let's go over the shapes. Let's try to define them. Z11 is going to be X, which is n by 1, times W, which has to be 3 by n, because it connects 3 neurons to the input. So this Z has to be 3 by 1. And it makes sense, because we have 3 neurons. Now let's go deeper. A1 is just the sigmoid of Z1, so it doesn't change the shape. It keeps the 3 by 1. Z2, we know it has to be 2 by 1, because there are 2 neurons in the second layer. and it helps us figure out what W2 would be. We know A1 is 3 by 1. It means that W2 has to be 2 by 3. And if you count the edges between the first and the second layer here, you will find 6 edges. 2 times 3. A2, same shape as Z2.
Same shit.
Z3, 1 by 1. A3, 1 by 1. W3, it has to be 1 by 2. Because A2 is 2 by 1.
Okay, they are like
And same for B.
linear functions.
B is
whatever.
going to be the number of neurons, so 3 by 1, 2 by 1, and finally 1 by 1. I think it's usually very helpful, even when coding this type of equations, to know all the shapes that are involved. Are you guys like totally okay with the shapes? Super easy to figure out? Okay, cool. So now, what is interesting is that we will try to vectorize the code even more. Does someone remember the difference between... We will try to vectorize the code even more. Does someone remember the difference between stochastic gradient descent and gradient descent? What's the difference?
What is the difference between?
What's the difference between stochastic gradient descent and gradient descent?
Okay.
What's the difference?
Stochastic and... Okay, in stochastic gradient descent and gradient descent. I think in stochastic gradient descent, we will go towards the gradient, but the size of the vector we go is just random, right? I don't know. I haven't had a stochastic gradient descent thing in my life before. It was just gradients.
Exactly. Stochastic gradient descent is updates the weights and the bias after you see every example. So the direction of the gradient is quite noisy, doesn't represent very well the entire batch, while gradient descent or batch gradient descent is update after you've seen the whole batch of examples. And the gradient is much more precise. It points to the direction you want to go to.
Oh, okay. So it was not what I said.
So what we're trying to do now is to write down these equations if instead of giving one single cat image, we had given a bunch of images that either have a cat or not a cat. So now, our input X. So what happens for an input batch? Of M examples. So now, our X is not anymore a single column vector, it's a matrix with the first image corresponding to X1, the second image corresponding to X2, and so on until the mth image corresponding to Xn. And I'm introducing a new notation, which is the parenthesis superscript corresponding to the ID of the example.
Huh?
So example, superscript, and I'm introducing to our X is not anymore our input X.
Focus.
So what happens for an input batch?
For an input batch, not patch.
Of M examples.
Of M examples. So we have M examples, we have M cats, and we call it an input batch. Like an input batch with an A. Input batch. And we have an, what happens to it?
So now, our X is not anymore a single column vector.
Oh, it's not a single, it's M column vectors next to each other. Makes sense?
It's a matrix
Mm-hmm.
with the first image corresponding to X1, the second image corresponding to X2, and so on until the nth image corresponding to Xn.
M.
And I'm introducing a new notation,
Completely
which
makes
is the
sense. So this is
parenthesis
the data,
superscript
input data. And we are,
corresponding to the ID
each sample
of
is a
the
column.
example.
What is it? ID.
So square brackets for the layer, round brackets for the ID of the example we're talking about.
Okay.
So just to give more context on what we're trying to do, we know that this is a bunch of operations. We just have a network with input, hidden, and output layer. We could have a network with 1,000 layers. The more layers we have, the more computation, and it quickly goes up. So what we want to do is to be able to parallelize our code or our computation as much as possible by giving batches of inputs and parallelizing these equations. So let's see how these equations are modified when we give it a batch of m inputs. I will use capital letters to denote the equivalent of the lowercase letters, but for a batch of input. So Z1, as an example, would be W1, let's use the same, W1 times X plus B1. So let's analyze what Z1 would look like. Z1, we know that for every input example of the batch, we will get one Z1. So it should look like this.
Mm-hmm. Yep.
Then we have to figure out what have to be the shapes of this equation in order to
W times X plus
we
B.
know that Z1 was 3 by 1. It means capital Z1 has to be 3 by M.
Yeah.
Because each of these column vectors are 3 by 1. And we have M of them. Because for each input we forward propagate through the network, we get these equations. So for the first cat image, we get these equations. For the second cat image, we get, again, equations like that, and so on. So what is the shape of X?
What is the shape of X? I will tell you. 128 times M.
N by N.
N by M.
What is the shape of W1?
Oh, I will tell you. 3 by N.
It didn't change. W1 doesn't change. It's not because I will give 1,000 inputs to my network that the parameters are going to be more.
3 by
so
N.
The parameter number stays the same.
3 by N.
I give more inputs.
3 by N.
And so this has to be
3 by N
in order to match 0. Now the interesting thing.
B1. It is 3 by 1. 3 by 1. 3 by 1.
There is
3 by 1.
algebraic problem here.
3 by 1.
What is the algebraic problem?
3 by 1.
We said that the number of parameters doesn't
3
change.
by 1. 3 by 1.
It means that W has the same shape as it has before.
W has the same shape.
B should have the same shape as it had before, right? Should be 3 by 1. What's the problem of this equation?
What is the problem of this equation? Actually, there is no problem. Just we are now like training our data on a bigger data set. Bigger data set.
Exactly.
Bigger data
We're
set.
summing
Bigger.
a 3 by M matrix to a 3 by 1.
Oh, yes, yes. So what I wanna suggest is just we need to replicate B. I don't wanna introduce new B's because I just wanna replicate
Vector.
B.
This is not possible in math. It doesn't work. It doesn't match. When you do summations or subtraction, you need the two terms to be the same shape because you will do an element-wise addition or an element-wise subtraction. So what's the trick that is used here? It's a technique called broadcasting.
Broadcasting. Oh, wait a second. We 3 by 1. We multiplied by 1 by M. 1 by M, and it's all 1. Broadcasting.
Broadcasting is the fact that you don't want to change the number of parameters. It should stay the same.
Broadcasting,
But we still want
broadcasting.
this operation
Broadcasting,
to
broadcasting,
be able
broadcasting.
to be written in parallel
Broadcasting,
version.
broadcasting.
So we still want to write this
broadcasting,
equation because we
broadcasting.
want to parallelize our code.
That's it.
But we don't want to add more parameters. It doesn't make sense. So what we're going to do is that we're going to create a vector b tilde 1, which is going to be b1 repeated 3 times. Repeated
M times.
m times.
Woo-hoo-hoo! M times, guys. Look at my mathematical skills. I had linear algebra in
So
my
we just keep the same number of parameters, but just repeat them in order to be able to write my code in parallel.
Matrix application, matrix
This is called broadcast.
application.
And what is convenient is that for those of you who the homeworks are in MATLAB or Python? MATLAB, okay.
Fuck
So
you!
MATLAB, no, Python.
Fuck you, bitch! I knew MATLAB, and they are now giving me MATLAB. Now every motherfucking company asks you for Python. Fuck you all!
Python. So in Python, there is a package that is often used to code these equations. It's NumPy. So
Okay, NumPy, I know, NumPy.
So NumPy.
Import NumPy as NP. Import
Basically
NumPy
numerical
as
Python.
NP. Let's start
Directly do the
machine
broadcast.
learning.
It means
Import
if you sum
NumPy as
this
NP. Let's
3
start
by
machine
m
learning.
matrix with a 3 by 1 parameter vector is going to automatically reproduce the parameter vector m times so that the equation works.
Machine learning.
It's called broadcasting.
No, guys, I need to wash my
That makes
pants.
sense? So because
What
we're
are
using this
these on
technique,
it?
we're able to rewrite all these equations with
It is
capital
the
letters.
time.
Do you want to do it together or do you want to do it on your own? We're using this technique, we're able to rewrite all these equations with capital letters. Do you want to do it together or do you want to do it on your own?
I want to do it together,
Who wants to do it on their own?
and I want to have to do it on my own.
Okay, so let's do it on their own. On your own. So rewrite these with capital letters and figure out the shapes. I think you can do it at home, where we're not going to do it here, but make sure you understand all the shapes, yeah.
Yes, I understand all the shapes. I understand all the shapes.
So the question is, how is this different from principal component analysis? This is a supervised
From component.
learning algorithm that will be used to predict the price of a house. Principal component analysis doesn't predict anything. It gets an input matrix X, normalizes it, computes the covariance matrix, and then figures out what are the principal components by doing the eigenvalue decomposition. But the outcome of PCA is you know that the most important features of your data set X are going to be these features. Here we're not looking at the features, we're only looking at the output. That's what is important to us.
Close one though, close one. Thanks for the person who asked the question.
So the question is, can you explain why the first layer would see the edges? Is there any intuition behind it? It's not always going to see the edges, but it's oftentimes going to see the edges because in order to detect a human face, let's say, you will train an algorithm to find out whose face it is. So it has to understand the faces very well. You need the network to be complex enough to understand very detailed feature of the face. And usually, this neuron, what it sees as inputs are pixels. So it means every edge
X.
here is the multiplication of a weight by a pixel. So it sees pixels. It cannot understand the face as a whole because it sees only pixels. It's very granular information for it. So it's going to check if pixels nearby have the same color and understand that there is an edge there. Okay, but it's too complicated to understand the whole face in the first layer. However, if it understands a little more than a pixel information, it can give it to the next neuron. This neuron will receive more than pixel information. It will receive a little more complex, like edges. And then it will use this information to build on top of it and build the features of the face. So what I'm trying to sum up is that these neurons only see the pixels, so they're not able to build more than the edges. That's the minimum thing, the maximum thing.
I can't.
And it's a complex topic. Like interpretation of neural network is a highly researched topic, a big research topic. So nobody figured out exactly how all the neurons evolve.
We don't understand how it works.
One more question
but
and then
it
we move on.
works.
So the question is how do you decide how many neurons per layer, how many layers, what's the architecture of your neural network? There are two things to take into consideration, I would say. First, nobody knows the right answer, so you have to test it. So you guys talked about training.
Guys. Machine learning is an art. You need to test and try.
Set, validation set, and test set. So what we would do is we would try 10 different architectures, train the network on these, look at the validation set accuracy of all these, and decide which one seems to be the best.
Validation.
That's how we figure out what's the right network size. On top of that, using experience is often valuable. So if you give me a problem, I try always to gauge how complex is the problem. Like cat classification, do you think it's easier or harder than day and night classification? So day and night classification is I give you an image, I ask you to predict if it was taken during the day or during the night.
Cat.
And on the other hand, you want to think if there's a cat on the image or not. Which one is easier, which one is harder?
Cat is harder, day and night is easier.
Who thinks cat classification is harder? Okay, I think people agree. Cat classification seems harder. Why? Because there are many breeds of cats. Can look like different things. There's not many breeds of knights, I guess. One thing that might be challenging in day and night classification is if you want also to figure it out in-house, like inside. You know, maybe there is a tiny window there and I'm able to tell that it's the day. But for a network to understand it, you will need a lot more data than if only you wanted to work outside. Different. So these problems all have their own complexity. Based on their complexity, I think the network should be deeper. The more complex usually is the problem, the more data you need in order to figure out the output, the more deeper should be the network. That's an intuition, let's say. Okay, let's move on, guys, because I think we have about, 12 more minutes?
We have 12 more minutes. We have 12 more minutes. I can make 12 more minutes. Let's go.
Okay, let's try to write the loss function.
Guys, we are finishing. Guys, we are finishing. Guys, we are finishing.
For this problem.
We are more than a half already. We are in the second part of the semester, so we are gonna finish it. Sri Lanka. Sri Lanka is a country, by the way.
So now that we have our network, we have written this propagation equation, and I will call it forward propagation. It's going forward. It's going from the input.
We want to add feedback. Feedback.
To the output. Later on, when we will derive these equations, we will call them backward propagation, because we're starting from the loss and going backwards. So let's talk about the optimization problem. Optimizing W1, W2,
B1, B2,
W3, B1.
So the art is in choosing the number of layers, the number of nuance. Then the rest is mechanical mathematics.
B2, B3.
We just do
We have a lot of
once
stuff
and
to
for the
optimize,
rest.
right? We have to find the right values for these. And remember, model equals architecture plus parameter. We have our architecture. If we have
Model equals architecture plus parameters. Architecture is kind of intuitive. Parameters, mathematics.
for parameters, we're done. So in order to do that, we have to define an objective function. Sometimes called loss, sometimes called cost function.
Oh, I have no idea.
So usually we would call it loss if there is only one example in the batch, and cost if there is multiple examples in a batch.
Loss and cost. One example it's called loss, multiple examples called cost.
So the loss function, let's define the cost function. The cost function J depends on y hat and y. Okay? So y hat is A3.
Difference in y hat.
It depends on y hat and y. And we will set it to be
Sigma
the sum
y minus
of the loss functions, Li, and I will normalize it, it's not mandatory, but normalize it with 1 over n. So what does this mean is that we're going for batch gradient descent. We want to compute the loss function for the whole batch, parallelize our code, and then calculate the cost function that will be then derived to give us the direction of the gradients, that is the average direction of all the derivation with respect to the whole input batch. And Li will be the loss function corresponding to one parameter. So what's the error on this specific one input, sorry,
it was me passing.
and it will be the logistic loss. You've already seen these equations, I believe. Something like that. So now, is it more complex to take a derivative with respect to j, like of j with respect to the parameters, or of L? What's the most complex between this one? Let's say we're taking derivative with respect to W2 compared to this one.
What is the difference? There is no difference.
Which one is the hardest?
I think J is easier because
Who
you can
thinks
write
J is the hardest?
No, I
I
don't.
think it doesn't matter.
I say it doesn't matter.
It doesn't matter. Because derivation is a linear operation, right?
Motherfucker.
So you can just take the
Yeah,
derivative
but
inside.
once-
And you will see
one
that if you
thing
know
is-
this, you just have to take the sum over this. So instead of computing our derivatives on J, we will compute them on L. But it's totally equivalent. There's just one more step at the end. Okay? So now we defined our loss function. Super. We defined our loss function, and the next step is optimize. So we have to compute a lot of derivatives. And that's called backward propagation. So the question is, why is it called backward propagation? It's because what we want to do ultimately
Finding the loss function
for
based
any
on finding the
n
weights and
equals
parameters
1
based on the
to
loss.
3, we want to do that. WL equals WL minus alpha derivative of J with respect to WL, and BL equals BL
Oh,
minus alpha derivative of J with respect to BL. So we want to do that for every parameter in layer 1, 2, and 3. So it means we have to compute all these derivatives. We have to compute derivative of the cost with respect to W1, W2, W3, B1, B2, B3.
oh, it is the gradient.
You've done it with logistic regression. We're going to do it with a neural network. And you're going to understand why it's called backward propagation. Which one do you want to start with? Which derivative? You want to start with the derivative with respect to W1, W2, or W3, let's say. Assuming we'll do the bias later.
What is the difference? I don't get it.
W what? W1? You think W1 is a good idea?
W3. I don't know. What is
I
it?
don't want to do W1. So I think we should do W3. And the reason is
Last layer.
because if you look at this loss function, do you think the relation between W3 and this loss function is easier to understand, or the relation between W1 and this loss function?
W3 because it is the last layer.
It's the relation between W3 and this loss function, because W3 happens much later in the network. So if you want to understand how much should we move W1 in order to make the loss move? It's much more complicated than answering the question, how much should W3 move to move the loss? Because there's much more connections if you want to compute with W1. So that's why we call it backward propagation. It's because we will start with the top layer, the one that's the closest to the loss function, derive the derivative of J.
Makes sense, dude.
With respect to W1.
So he thought so amazing good.
Okay? And once we computed this derivative, which we're going to do next week, once we computed this number, we can then tackle this one.
Tackle.
Oh, sorry, yeah, thanks. Thank you. Yeah, once we computed this number, we will be able to compute this one very easily. Why very easily? Because we can use it.
Why? Because I will tell you why. So because we can use the combination of function, like rho JW3 is rho JW2 is rho JW3, W3, W2.
Calculus. So let's see how it works. I'm just going to give you the 1 minute pitch on backprop, but we'll do it next week together. So if we had to compute this derivative, what I will do is that I will separate it into several derivatives that are easier. I will separate it into derivative of J with respect to something, with this something, with respect to W3. And the question is, what should this something be? I will look at my equation.
Y, right? It is Y?
Equations. I know that J depends on Y hat.
Y hat.
And I know that Y hat depends on Z3. Y hat is the same thing as A.
Sigma.
I know it depends on Z3.
Yeah, okay.
So why don't I include Z3 in my equation? I also know that Z3
It's
depends
not
on
difficult.
W3.
It's not difficult.
And the derivative of Z3 with respect to W3 is super easy.
It's not difficult.
It's just A2 transpose. So I will just make a quick hack and say that this derivative is the same as taking it with respect to A3, taking the derivative of A3 with respect to Z3, and taking the derivative of Z3 with respect to W3. So you see, same derivative calculated in different ways. And I know these are pretty easy to compute.
Finish it, I
So
wanna
that's why we call it
go!
backpropagation. It's
3
because
more
I will use the
minutes,
chain
3
rule
more
to compute the
minutes,
derivative with
3
W3.
more
And
minutes.
then when I want to do it for W2, I'm going to insert the derivative with Z3 times the derivative of Z3 with respect to A2 times the derivative of A2 with respect to Z2 times derivative of Z2 with respect to W2. Does this make sense that
This
this
makes
thing
sense. This makes
here
sense. This makes sense.
is the same thing as this? It means if I want to compute the derivative of W2, I don't need to compute this anymore. I already did it for W3.
Ah, okay.
I just need to compute those, which are easy ones. And so on. If I want to compute the derivative of J with respect to W1, I'm not going to decompose all the thing again. I'm just going to take the derivative of J with respect to Z2, which is equal to this whole thing.
Oh, okay.
And then I'm going to multiply it by the derivative of Z2.
Alright, very good. So we
With
don't need to
respect to
compute
A1
everything 10 times.
Times the derivative of A1
It's like a
with respect to
layer of
Z1
simplification.
times the derivative of Z1 with respect to W1. And again, this thing, I know it already. I computed it previously just for this one.
Very
So
good.
what's interesting about it is that I'm not going to redo the work I did. I'm just going to store the right values while backpropagating and continue to derivate. One thing that you need to notice, though, is that, look, you need this forward propagation equation in order to remember what should be the path to take in your chain rule. Because you know that this derivative of J with respect to W3, I cannot use it as it is because W3 is not connected to the previous layer. If you look at this equation, A2 doesn't depend on W3. it depends on Z3. Sorry, like, my bad. It depends. No, sorry. What I wanted to say is that Z2 is connected to W2.
The
But
rest
A1 is not connected to W2. So you want to choose the path that you're going through in the proper way so that there's no cancellation in these derivatives. You cannot compute derivative of W2 with respect to A1. Right? You cannot compute that. You don't know it. Okay, so I think we're done for today. So one thing that I'd like you to do if you have time is just think about the things that can be tweaked in a neural network. When you build a neural network, you're not done. You have to tweak it. You have to tweak the activations, you have to tweak the loss function. There's many things you can tweak, and that's what we're going to see next week. Okay, thanks.
All right, guys, that was amazing. I loved today. We learned something new. It just feels so good when you learn something. Have a good day, guys. I love you.